Solve for u. The absolute value of u is equal to 7. I'm going to explain this a little bit differently. I'm going to actually use transformations to explain this. And so I'm going to write the absolute value of, let's say, u minus 0 is our center. And it's equal to 7. So we need to find, what this really says is find all the u values centered at u equals 0 that are exactly 7 units away. So visually, all you gotta do is draw a u number line, and it's centered at 0. And what's exactly 7 units away, or 7 distance units away? Well, it's either 7 or it's either what? -7. So those are your two answers. And we're going to shade only those two answers by symbolizing it with a solid dot on the number line. Now, from an algebra point of view, what would you end up writing? You would just write the absolute value of u equals 7, and then 2 steps later, you get u is now equal to positive 7 or u equals -7. So some of you might even write it like this, u equals plus or minus 7. I'm actually not going to write that. I'm just going to leave it as that. Let's circle our final answer. There it is. Let's solve this equation with an absolute value. The key to solving any equation with an absolute value is isolate that absolute value. And typically we isolate it on the left side of the equation. Why don't we do what's instinctively natural? We would subtract 15 to both sides, and we get what? The absolute value of 6y minus 3 is now equal to what? 57? Yeah, 57. Now, what's the rule with the absolute value? If you have the absolute value of m is equal to b, the next step we could write is m equals b, or m equals the opposite of b. Let's do that. 6y minus 3 is equal to 57, or what? 6y minus 3 is equal to -57. Why don't we add 3? And not surprisingly here, we get y is equal to 60 divided by 6, which is 10. Or, what happens on this side? Add 3, we get -54, so y is going to be -9. So we actually have two answers for y. You could check it in the original equation if you want. You know, you can just check to see if that makes the original equation true. I'm going to circle the final answer. You're probably wondering why this is true. If you have this initial step, why are these two steps correct? Let's look at the definition of absolute value. Definition. It's actually two parts. If x is greater than or equal to 0, then the absolute value of x is simply x. If x is less than 0, then the absolute value of x is called the opposite of x. So looking back at this, absolute value of m is equal to b implies two situations. If m is greater than or equal to 0, then m equals b. What's the second situation? If m is less than 0, then the opposite of m is equal to b. So there's really two cases, and those two cases are separated by an or. And here's an or down here. So notice those ors match with what I wrote over here as well. The ors are necessary. These are called disjunctions. If you're into computer science, the word or and and are very, very important. They're important in computer science, and they're very, very important in English as well. Solving a compound linear inequality. Solve the compound inequality. 3x plus 2 greater than 11, or 3x minus 2 is less than negative 11. Let's see what we can do with this. First thing I'm going to do is just recopy it so that I have more room. The key word here is or, and or is a disjunction in computer science. This is what we call an inclusive or in mathematics, okay? Not an exclusive or. That's actually a different kind of or. We're going to do an inclusive or. What's an inclusive or? Like if I said, I live in California or I live in Nevada, if one of those two statements is true, then the entire sentence is true. So we're actually increasing the possibilities of a true statement. So that's why we call it an inclusive or. We're including more possibilities. Let's subtract 2 now. Subtract 2, subtract 2. And then we get 3x is now greater than 9. Or what happens for this inequality? Now, or we have 3x is less than negative 9. Let's divide the entire sides by 3. Because 3 is not 0. And finally, we get this disjunction, x is greater than 3, or x is less than negative 3. And how do we graph that on a number line? Well, technically speaking, we should write this in the order of a number line from left to right. So it's better to read it like this. And then we're going to write the interval notation after we draw it. So how do we draw this? You draw a x number line. And from left to right, I'm going to shade the arrow. So I'm going to shade the concept of negative infinity and go all the way up to what? Parentheses negative 3. And then when do we start back up again? Well, we need all the x values that are more than 3. So I'm going to shade 3.1, I'm going to shade 4, I'm going to shade 2000, and I'm going to shade all the way up to the concept of infinity. So there's a concept of negative infinity there, and there's a concept of infinity if you're reading the number line from left to right. Remember, what kind of number line is this? This is the x number line. Finally, interval notation. We just take it from the picture, negative infinity up to negative 3, parentheses, to symbolize that we do not include negative 3, union, parenthesis, to symbolize that we do not include 3, and then we run this all the way to the concept of positive infinity. Let's circle our final answer with our interval there. It does ask for a graph, so let's circle our graph as well. And also, the work is very important. Make sure you could show the work to justify your answer. All right, let's do example B. This time, instead of a disjunction, we have a conjunction. And that is, we're going to look for commonality or an intersection here. Let's write 4x plus 3 greater than or equal to negative 21, and 2x plus 4 is less than or equal to 16. We're going to keep that word and throughout. 4x greater than or equal to negative 24, and 2x is less than or equal to positive 12. There we go. Divide these entire sides by 4, divide these entire sides by 2. 4 is not 0, 2 is not 0. X is greater than or equal to negative 6, and x is less than or equal to 6. This time, we have a conjunction, and let's order this from left to right. Actually, it is ordered from left to right. If this is an and, sometimes it's nice to combine it like this. Negative 6 is less than or equal to x, and x is less than or equal to 6. This is also an equivalent statement. But let's just graph this right here. We need all the x values that are greater than or equal to negative 6, and less than 6. So we could shade negative 5, we could shade negative 3, we could shade negative 5 and 9/10. And then we keep shading until we get to where? Until we get to 6. Now, what's my mistake right now? Can you see it? Well, there's an equal sign. We need to shade 6 as well. So instead of putting a parentheses, we symbolize that with a bracket. The bracket will actually symbolize that we will shade positive 6. The bracket here will also symbolize that we will shade negative 6. So we shaded the true region. And let's write our final answer in interval notation. We simply take it from the picture, from left to right, bracket, negative 6, comma, 6, bracket. And we're done. Let's circle our final answers. It asks for a graph. And of course, we're in a course where we need interval notation. Also circle your work. Once again, your work is pretty important. It justifies how you got to the final answer. Solving an absolute value inequality. Inequalities are very, very important in subjects like statistics and calculus. They actually show a range of values. And remember, for any inequality, you're just looking for the true region. You know, what y values will actually satisfy this original inequality. And over here, what x values will satisfy this original inequality? These problems might look similar, but they're actually completely different. So I recommend that you take very, very careful notes here. Just because of this symbol right here, greater than or equal to changes the procedure of this symbol right here, which is less than or equal to. With absolute value inequalities, the first step is to isolate the absolute value on the left-hand side of the inequality. Let's begin with that. Let's subtract 15, and now we have isolated the absolute value of 4y is now greater than or equal to 7. Now from here, things get a little bit tricky. This procedure changes completely compared to example B. So take very, very careful notes. 4y is greater than or equal to 7, or the opposite of 4y is greater than or equal to 7. What does that mean? That means that y is greater than or equal to 7/4, or y is less than or equal to negative 7/4. Remember, if you divide by a negative in the middle of an inequality statement, we actually change the order of that inequality. In other words, we switch the sign. If you divide by -4 here on both sides, we switch the sign on the very next step. Now let's write this from left to right on a number line. So from left to right on a number line, this really says y is less than or equal to negative 7/4, or y is greater than or equal to 7/4. Now we're ready to graph this. Let's draw a y number line, and we're going to shade this from left to right. From left to right, we could shade the concept of negative infinity. So we shade it by that arrow there. And then we shade all the y values all the way up to what? All the way up to bracket -7/4. When do we start this back up again? When we get to +7/4, we need to shade 7/4 and then shade all the way to the right. And we need to include the concept of infinity. Let's state our final answer in interval notation. -infinity up to -7/4, bracket, union, 7/4, up to concept of infinity. And there is our final answer in interval notation. Now, how does the procedure in example B changes? It changes drastically. First thing we're going to do is once again isolate the absolute value onto the left side of the inequality. So far we have 4 times the absolute value of x minus 1 is now less than or equal to 24. 4 is not 0, so we could divide the entire size by 4, and we get the absolute value of x minus 1 is less than or equal to 6. Absolute value. This statement is completely different than the one in example A. With this, we actually say -6 is less than or equal to x minus 1, and x minus 1 is less than or equal to 6. Let's get the x's by themselves, and we get -5 is less than or equal to x, and x is less than or equal to 7. Another way to interpret this is at this line right here. It says find all x values centered at where? Centered at x equals 1 that are within 6 units. Within 6 units, or 6 distance units. And we could include 6 as well. So either 6 units, within 6 units, or exactly 6 units away. Why don't we draw that? So if you drew this on the x number line, our center is actually what? Our center is actually 1. And we want to shade all the x values that are within 6 units away or exactly 6 units away. So that means we got to include 7, and we got to include, on the left hand side, we got to include -5. Well, yeah, that's the answer stated right above. And we got to shade, we could shade what? We could shade -1, we could shade 2, we could shade 5. Can we shade 89 though? We can't shade 89. Final answer in interval notation, -5, comma, 7, and then make sure you have brackets. Solving a radical equation. I'm going to solve for x here. And the first step in solving a radical equation is isolate a radical on one side. Let's subtract the square root of x plus 4 on both sides of the equation. It's nice and balanced. We get a new equation. The square root of -3x minus 8 is now equal to 2 minus the square root of x plus 4. Now we're going to square the entire sides. Square this side, and then we're going to square this side. Now remember, a minus b quantity squared has a formula. It's a squared minus a times b, and then double it, and then plus b squared. Let's automatically compute this. Parentheses x plus 4. All right. Let's try to collect like terms, and then once again isolate the radical on one side. So subtracting 8 and subtracting x. All right. I'm going to actually factor out a negative 4. So we get x plus 4 here equals negative 4 times negative 4 times the square root of x plus 4. Negative 4 is not 0. So we're going to divide the entire sides by negative 4. Now I do like my square root symbol over here instead. So I'm going to turn this equation around. And we have x plus 4. So we've isolated the radical again. And now we will square the entire sides. Now we get to use the other formula, very similar formula. A plus b quantity squared is equal to a squared plus a times b and then double it, and then plus b squared. We have x plus 4 on the left-hand side of the equation, and we have x squared plus 8x plus 16. Now we have a quadratic equation, and we know what to do with this. We set the equation equal to 0. This factors nicely. Always check your factoring. I've checked it. Now this says x plus 4 is equal to 0 or x plus 3 is equal to 0. X equals negative 4 or x equals negative 3. Now we got to check our solutions. So we need to check our original equation. Our original equation is here. The reason why we have to check our equation is that when you square both sides on an equation, you might get something called an extraneous solution, or in other words, it's not a solution at all. It's just some extra number within our process. So why don't we check negative 4 into triple star? So let's check negative 3 times negative 4 minus 8 with a square root symbol on top of it, plus negative 4 plus 4, and we want to know what this is. So this is an expression. We have 12 minus 8, which is the square root of 4, plus 0. This actually is 2, which is the right-hand side of that equation. So yes, this checks. So x equals negative 4 is really a solution. Why don't we check the other one? What's the other check? We got to check negative 3. Negative 3 times negative 3, subtract 8, plus negative 3 plus 4. And let's see what this is. This is 9 minus 8, so square root of 1, plus another square root of 1. In our case, 1 plus 1 does get us 2. And so this checks as well. Yes. And so we're going to circle this one. This doesn't always check though. So whenever you solve a radical equation, make sure you check your answers by substituting it back into the original equation to see if it gives you a true statement. True. And then this one was true as well. Make sure you're able to replicate all the work. So it doesn't hurt to circle your work, but make sure you somehow indicate your final answer. Maybe you give it the abbreviation FA or something. Final answer. And then right here, final answer. Let's solve this radical equation. The first thing you want to do when you're solving radical equations is isolate one of the radicals. Let's subtract the square root of u plus 1. Remember that when you're solving equations, you're trying to find the value of the missing variable that makes the original equation true. That is our goal. We're trying to find values of u that makes the original equation true. Now that we've isolated a radical, we're going to square the entire sides. And you got to remember, a minus b quantity squared is square the first term, then do a times b, double it, and subtract it, and then square the last term. So we get a perfect square trinomial. Let's see what we get here. Negative 5u plus 16, and now we have 9. We're going to do 3 times the square root of u plus 1, double it, and then subtract it, and then square the last term. When you square the last term, you simply get plus the quantity u plus 1. We want to isolate the radical again, so let's collect like terms, simplify this, just react to it. You've done this probably a billion times, not a big deal. And we want to isolate the radical again. Negative 6u plus 6 is equal to negative 6 times the square root of u plus 1. I'm actually going to factor out a negative 6 on the left-hand side of the equation. And that way I could divide the entire sides by negative 6 because negative 6 is not 0. And what do we get? I'm also going to turn this around. I'm going to get the square root of u plus 1 is equal to u minus 1. Let's square the entire sides again. And we get u plus 1 is equal to u squared minus 2u plus 1. And this is a quadratic equation. We know what to do with those. We want to write another equation set equal to 0. So we get u squared minus 3u. That's it, is equal to 0. Greatest common factor is u, and then we have u minus 3. So either u is equal to 0 or u is equal to 3. Now we got to check our answer, because when we square entire sides in an equation, we might actually produce extra numbers. We don't want those extra numbers. We only want the numbers that make the original equation true. So I'm going to go back to the original equation. I'm going to mark it triple star. I'm going to go back to triple star, and let's start with u equals 0. Let's substitute u equals 0. Negative 5 times 0 plus 16 plus square root of 0 plus 1. We want to see what this really is. Let's simplify this expression. This is the square root of 16 plus square root of 1. Well, that's just 4 plus 1. That gets me 5. Is 5 3? 5 is not 3. So the original equation here is false. In other words, u equals 0 is not a solution. Let's check the other number. What's the other number we have to check? We have to check u equals 3. So negative 5 times 3 plus 16 plus square root of 3 plus 1. Let's simplify this expression. This is the square root of 1 plus the square root of 4. That is 1 plus 2. That does get me what? That does get you 3, which is what we want on the other side of the equation. So this makes the original equation true. 3 makes the original equation true, and that's what we were looking for. So we finally get the circle u equals 3. Now all your work needs to be included as well, so might as well just circle the entire page. And we can indicate this with the final answer, FA. Inverse functions. We're going to talk about a quadratic function and the square root function and how sometimes they're inverses of each other. You want to think inverse functions as being able to retrace your steps. So if you typed in a destination on Google Maps, there's always that to and from feature. Well, if you switch that to and from feature, well, that is called an inverse function. From an algebra point of view, we are going to do that. We're going to try to reverse our steps or retrace our steps by finding the inverse function. Consider the f of x. Consider the function f of x equals x squared plus 8 for this restricted domain. Include 0 and then run it to the concept of infinity. Now, you could even do a quick sketch of this graph. So you have a function here that is a basic parabola shifted 8 units up. So that is 8 units up. We want to find its inverse. And remember, to find its inverse, we actually just flip it across the y equals x line. So if you flip it, the inverse should look something like this. Something like that. And that actually looks kind of like a what kind of function? It kind of looks like a square root function. Okay, so how do we find inverses? We take the original function, we name the outputs to be y. Now we're going to take a different equation by switching the input and output. Okay. So switch the y's and the x. Our new equation will look something like this. X is now equal to y squared plus 8. And our goal is to solve for y. So subtract 8, and we get y squared is equal to x minus 8. Now we take the square root of both sides. When you take the square root of y squared, you just get absolute value of y is now equal to the square root of x minus 8. But how do you solve an absolute value equation? Well, you either get y is equal to the square root of x minus 8, or y is equal to the negative square root of x minus 8. So which one is this? Well, it can't be the second one. Notice that from your quick sketch of your graph, which one matches? This sketch here matches with that one. Just by understanding your basic graphs. Whereas this one here does not match. So if this one matches, we're going to take this function and rename it. What are we going to rename this to be? We're going to replace that y with a symbol. And that symbol is called the inverse of f of x. So the inverse of f of x is now equal to the square root of x minus 8. We also need to state the domain. The domain is what? On 8 parenthesis to infinity. Now I did that really quick. How did I get that? Let's look at the domain of the inverse of f of x. Remember, you can only take the square root of what kind of numbers? Positive numbers, and that gives me my domain. Let's circle our final answer. Don't forget to rename your function. You have to write back the function notation. You have to write the f superscript -1 of x. The other thing you want to realize is this is not an exponent. This is just a symbol. It's like a birth certificate. This is just a superscript of a negative and a 1, but it's not an exponent. Inverse functions. You want to think of inverse functions as getting from point A to point B. But in computer science, a lot of times we need to retrace our steps. So it might be wise to be able to find a way to get from point B to point A. So a lot of times if we have algorithms in computer science, we also need the inverse algorithms. So think of algebra as doing that, okay? Some functions that we could actually reverse or reverse back, then we call those inverse functions. Here's a one-to-one function. Remember that inverse functions exist for one-to-one functions. H of x is equal to 5x minus 2 over x plus 9. We're going to find the inverse of h of x. State the domain and range in interval notation. I'm going to first recopy the problem. H of x is equal to 5x minus 2 over x plus 9. We're going to say the output is going to be renamed to be y. In order to find the inverse function, we're going to switch the order. We're going to switch the order of x and y. And how do we do that? We simply replace x with y and replace y with x. So here's our new problem. I'm going to draw a line there. X is here. And now we have 5 times y minus 2 over y plus 9. Now the goal is to solve for y. If we solve for y, we just need to collect like terms and get y by itself on one side of the equation. That's a minus 2. I think I'm going to have 9x plus 2 on the left-hand side of the equation. And on the right-hand side, I'm going to get 5y minus an xy. Yeah. 9x plus 2 is equal to y times 5 minus x. Now here's an issue. We got to make sure 5 minus x is never 0. Now we could divide the entire sides by 5 minus x. And we get y is equal to something. Y is equal to 9x plus 2 over 5 minus x, where 5 minus x is not 0. That's another way of saying x is not equal to 5. We got to make sure we rename y. What are we going to rename y? We're going to rename y to be the inverse of h of x. We got to give back the function notation. Our goal is to find a domain. The domain of the inverse of h is equal to negative infinity up to 5 union 5 up to the concept of infinity. We also need to find the range. So keep in mind there is a horizontal asymptote here. The horizontal asymptote for the inverse of h is y equals negative 9. And you can see that because the coefficients are right there. Now I'm going to remove that 1 There it goes. So we see the horizontal asymptote is y equals negative 9. So what does that mean for our range? Range of the inverse of h is equal to negative infinity, parenthesis, up to negative 9, union negative 9 to infinity. Let's circle our final answers. We got the inverse, we got the domain of the inverse, and we got the range of the inverse. Translating the graph of an exponential function. Here's a graph showing exponential growth. It started off with very little amounts, and then once it hit the y-intercept, it spiked rapidly. Make sure you see the arrows. And so in some cases, when you draw this on your own paper, make sure you draw the arrows there. That way it matches the domain and range. We are going to pick on a certain ordered pair here. We're going to pick on that ordered pair 0, 1. We also need to know that exponential functions have horizontal asymptotes. So the other thing you want to draw on your paper is you want to draw and label your horizontal asymptote, because we are going to relabel this very, very soon. The horizontal asymptote here is y equals 0. Now, according to this, the horizontal asymptote is going to move 2 units up, because all your y values are going to go 2 units up. So add 2 units to every y value. If we add 2 units to every y value, instead of getting 0, 1, we get 0, 3. And then we're going to move the horizontal asymptote as well, 2 units up. So the horizontal asymptote needs to be relabeled. Make sure you relabeled your horizontal asymptote to be y equals 2. And now we're able to draw. Wait, I'm sorry. We need to do one more thing to the x value. We're not only just moving it up, we also have to move it to the right 4 units. So I'm going to move it right 4 units, and then we could plot the ordered pair. So there's actually an ordered pair at 4, 3. Not the 0, 3 that I mentioned earlier. So let me erase that. There it goes. Now we're in good shape. Let's draw the new function. The new function goes something like this. Remember, you're drawing this on your own paper. Draw this on your own paper before you actually submit the graph. So let's recap what took place. You took an x and then 3 to the x, and you took that 0, 1, and you actually translated that. How are we translating that? We're doing a lot of things. We're doing 2 translations. And so first thing you're going to do, you're going to go right 4 units for the x value. And then for the previous y value, you got to add 2 units. So you end up getting 3. So that's why you're plotting an ordered pair at 4, 3. Make sure you relabel your horizontal asymptote, which is y equals 2. So these labels are necessary. Show your work. And then your final answer is actually indicated with the graph in red. Let's try this again with example B. Once again, put the arrows there. Name your current horizontal asymptote. Your current horizontal asymptote is y equals 0. And our goal is to move this ordered pair here, 0, 1. How are we going to move it this time? we're going to move it left 2 units to the x values. So that's -2. And then for the y values, it says to go down 4 units. So this should be -3. And what is our new function? Our new function is called 1/3 raised to the x plus 2, and then subtract 4. So that means we need to move our horizontal asymptote. Our horizontal asymptote is down here. Make sure you label it on your own sheet of paper or graph paper. So y equals -4. Draw your horizontal asymptote first. Then draw your new ordered pair, which is -2, -3, right here. And draw your graph, which is still an exponential decay. Like that. Once again, gotta label your horizontal asymptote if you want to receive full credit. Gotta label your ordered pair, your new ordered pair. And then, of course, the graph. Your final answer is displayed in the graph above, which is the red graph.